something here, or I can make some changes here and there, but then once I fix the ingredients, I have to go and enter another important thing in physics, which are right-handed neutrinos. Now, for the, I'm sorry for the physicist. I may say things which are well known to the physicist, but Fermi said, never underestimate the pleasure of learning things that you already know. Right-handed neutrinos. Now, they are the most recent addition to the zoo, particle zoo, and we have not seen them, but we know that neutrinos oscillate between the various families, electron, muon, and tau neutrino. I said that there are 3 copies. They can transmute one into each other, and this is only possible if neutrinos have mass. So we know that neutrinos have mass. If neutrinos have mass, then they must come with both chirality, left-handed and right-handed. And I was using right-handed neutrino because my representation was allowing for it. And so we don't have a direct calculation, but the mass is very small. It's 0.12 electron volt. It's smaller than 0.12 electron volt and 0. So we know that they are there, but we have limits on their mass because we look for them and we don't find them. And now, this is so a little less than that is the mass of the lightest neutrino. The electron, which is the next slightest, is half of a Jeff, but I'm writing just with the same thing. So it's 500,000 and more. It's 5 million times larger than this number. So they are very, very light. And the origin of numerical values of all masses in the standard model are mysterious. No one knows why. That there is no, in fact, if you get one of them or a relation between one of them, you get a Nobel Prize. There are a number of Nobel Prizes to be won there. If you get all of them at the same time, you can bet. However, this suggests that the mechanism to give the mass is probably different. Because, then from this one you somehow go growing to 150 GeV in a sort of, not continuous gap, but there are no gaps so high. And I didn't know anything. Oh, okay. It's not my fault. So it's called there's a mechanism called the seesaw mechanism to give a high Majorana mass to the right-handed neutrino, in addition to the usual Dirac mass. Now let me say what these different masses. As I said before, the mass in the Dirac equation appear like that. So I take the left-handed antiparticle and I connect to the right-handed particle. But it's possible to have also this kind of thing, this kind of mass. This is possible. Not for every particle. It would create some problems. For neutrinos, that's why I put a new here, it's possible to have a Majorana mass. And it's not known whether the mass of the neutrino is Majorana as Dirac or Majorana. The one above is Dirac, the one below is Majorana. It's likely to be Majorana because the right-handed neutrino is different from the left-handed. So there must be some Majorana masses. Because this, of course, this I put right, but I could put left. If I put only right, then you get a Majorana mass. Now there is a mechanism which gives Majorana masses, but then it enables to give a very large mass to the right-handed neutrino and a very small mass to the left-handed neutrino. And okay, actually I here. so those are the possible Majorana masses. So in general, a mass, instead of being a number, becomes a mass matrix, because I can have the mixing of the two. See, this is a diagonal part if I have put left and right in a vector, and this is diagonal part. In case of generations, the matrices are not 2 by 2, they will be 6 by 6, but the idea is the same. The eigenstate of mass are obtained by diagonalizing the matrix. So what you actually measure is the diagonalization of this by 2 matrix. The seesaw mechanism assumes a matrix in which there is a Majorana mass for the right-hand neutrino of the very large, of the order of the unification scale. This was 10 to the 15 GeV, so very large. And a normal, smaller Dirac mass. One of the eigenvalues of this matrix, so, will be very large, while the other will be very small. Okay, this is just a fact of 2 by 2 matrices. If you put large off-diagonal numbers, then when you diagonalize, you get one very large eigenvalue and one very small eigenvalue. And that's what is believed to be happening. Now, it turns out that while the constraints of non-homogeneous geometry are quite stringent, it turns out that the slot corresponding to a Majorana mass matrix is allowed. So in this 96 by 96, it's of course, each slot is a coupling of this kind. And as I said, you cannot put numbers everywhere, because then when you start commuting, you can get anything. So, so you can put a Majorana mass matrix for right-handed neutrino. And now we have another large scale in the model. So I can put a number there, and this number is can be anything. So I have freedom to put another number. This number has not been measured. So, so this will change the running of the beta function, and cause on one side cause these three lines to come together, because now neutrinos will play a role, because at high energy they will appear, and on the other side will give a different value for the X mass. So I have different one-forms, different bosonic fields. Now, unfortunately, if you do an explicit calculation, shows that this extra term in df commutes with the algebra, and therefore doesn't give an extra boson, and just a neutrino. Neutrino doesn't interact with anything. So I can put the mass of the neutrino there, but the running of the tree is not changing. And I don't get a boson, because that term there, that slot there, is such that when I take the commutators with the algebra, I get 0. So we can put something there, and now we can do we can do a number of things. So this consideration suggested to Shamseddin and Kohn to consider this extra field the extra slot to be a field. Now this has the property of the X, and it couples to it and changes the running. And this field actually will be another boson put by hand. It had appeared in the literature when it was realized that the relative X field creates a dangerous instability in cosmology. So this had been considered by phenomenology. So what was happening to this running was already known before. Phenomenologists explore about that, since they have no constraint, they can put anything they want, and if somebody puts something there. But that time, nobody liked it, except Shamseddin. Shamseddin keeps liking it. Because all the bosons are in one forms, which are obtained by commuting with dA or with D. And they are in dA. So we obtain the W's, the Z, the photons, the gluons, and the X. Now putting the X, why do you put a field by hand? The good thing is that all the fields, the bosonic field, were coming from the commutator. So it's true you can put something there, because since this commutes with everything, you can put in something there. But then the good thing is that everything is fixed.
So mathematically, I mean, from the point of view of spectral triple, what does it mean to say that you are adding a field?
What I'm saying is that one of the entries in the yes, when I write this DF,
right,
which I said is a matrix of numbers, there instead of being a matrix of numbers, in that spot there is a function of x.
At one entry.
Yeah. So I have this DF. Okay, this DF is that's how. So let's say that I have here the electron, right, up, left, up, right, and a vector, 90, label of 96. Here, right, and here I have this huge matrix. Okay, those are labels. So at this point here, I have the mass of the electron. And actually symmetric, so I have the mass of the electron. And it's a number. I should probably say Yukawa kappa, but it's a number. Then this is DF, no? And so I have this thing of numbers. Now, I can have a point in which here there is right-handed neutrino, right-handed neutrino, and here I put something which depends on x. That doesn't disturb me, because when I take the commutator of this with the finite representation of the algebra, this slot here is such that it commutes with everything. So I can put, if I put a field here, then I create an incredible mess. So I can put a field here. However, it's very nice to have that this is numbers, and all of the fields, bosonic fields, come from the commutator. So then you have to explain why there is a field there. Okay?
So this is a function of m, on m, right? So, so m being the
manifold, yes. It's a function of space-time. Okay? So a function of space-time is what we call a field. Okay? It will be another extra scalar field, which is put by hand there. So we should ask more to the model and go back to its roots. And in order to go back to its roots, there are, I have to look at the algebra, and I can see which non-commutative C-star algebra satisfy the conditions. Now, and this is, I will present this concept, give the solutions, and then we'll finish, and then tomorrow we'll discuss Lorentz. So, you can ask what finite dimensional C-star algebras are manifolds. So a C-star algebra is necessarily a sum of matrices of the real, the complex of the quaternions. A finite C-star algebra is always of this kind. Now, you can ask, you can ask which algebra satisfy the conditions to be a manifold. Do you remember these 7 axioms? They were algebraic. So this is again, is in the paper of Conner Marcolli, it's finite algebras. So if I have to commute with something, with you know what chirality is, because this is, you know what are the left-handed, you know what the J is, and so which algebras will satisfy this? And you find very interestingly that only a certain kind of algebras will satisfy this condition. And they are A by A quaternionic matrices plus 2A by 2A complex matrices. Since a quaternion is a 2 by 2 matrices, they are both 2A by 2A matrices with a fixed state, with integer A. And so they are matrices of the same size. And they are to be represented on an Hilbert space of 2 times 2a square dimensions, and then I can replicate it with generations.
The extra factor 2 is because of the chiral thing?
Because of the chiral thing, exactly. So, the algebra is made of unitary operators and the symmetry will be broken, so this will reduce the gauge group. So there is very little freedom in this game. It must be something of this kind, or something which I can write as a sub-algebra with a breaking mechanism of this. And so it has to act 2 times 2a. So for a non-trivial grading, a must be larger than or equal to 2. So we just look at M2 of A plus M4 of A. The Hilbert space is dimension 32. Bingo. We had nature as dimension 32. So we can use this A with A's too. And we need right-handed neutrinos. Okay, so before right-handed neutrinos, we couldn't do this one. Now I want to impose this, the fact that chirality commutes with the algebra. And so I have that my algebra now is quaternions plus quaternions plus M4 of P. Now, if I impose another condition, I break this to the standard model. I break to the algebra of the standard model, 3 by 3 matrices. But before, if I don't do yet this, the physicist of a certain age in this room will recognize that the unitaries of this are SU2 left times SU2 right times SU4. This is Petit-Salam model. Okay? So naturally you end up with Petit-Salam model. Petit-Salam model was one of the first, if not the first, unified model. So it was taking the standard model but unifying the interaction. And the idea is that we have 3 colors, and then leptons have no color. But Petit-Salam put the lepton number as the 4th color. So this is a unified, a larger group, which existed, but I think is in the 70s. So we have this unified. There is a 4th color. Now this breaks to the standard model. Now in order to things with break, the breaking is done by a field. The X field breaks SU2 cross U1 down to U1, but you need something which breaks SU2 cross SU2 cross SU4 to SU2 cross U1 from SU3. And this you can do with a field, and this field is called sigma or rho, and that's the analog of the X. It's the higher level X.
So is it that sigma?
It's exactly that sigma, yes. So I have to get this thing out. This sphere appears here in the position, and we can put this here. But now cranking the machine does not produce it. So you have to make some slight changes. However, if you do the running, let me do this there. If you do the running with this extra field, whose parameter somehow the one that you get from getting the right seesaw mechanism, masses of the mechanism, then you have freedom because this number is not precisely defined, but is not totally arbitrary. So you more or less know in which bracket it should be. If you do this, then you get the right mass of the X. However, the point is that you don't get it in the usual way, so you can avoid putting this by hand, and there are 3 ways in which this can be done. One is to enlarge the Hilbert space, introducing new fermions and new interaction, and this was done by Christoph Stefan before the finding of the X, before Conrad Marcoli was studying this. However, enlarging if you put more fermions, you have a lot more freedom. And so in general, we tend to say the fermions are the ones that they are. And no one has seen them, and they will be, there is a cancellation of anomaly issues. Then myself and Agostino De Fazzato and Pierre Martinetti increased the symmetry. So instead of having manifold is something of this kind. Standard model is with A equal 2, but you can take A equal 4 and you do what we call a grand symmetry, not a grand unified symmetry. And then Shamseddin-Kohn and Vasilyakov instead introduce a violation of the order 1 condition. So they put objects, they put numbers in forbidden place with the order 1 condition, and then they managed to do that. Also, I don't like this because I like the fact that you keep all the conditions of being a manifold. But of course, the conditions were made by Alan Kohn, and he can break whatever it is. I wouldn't dare doing it, but let me just say in the last less than 5 minutes something. So we have this grand symmetry. It's not a grand unified theory. Usually, the traditional grand unified group like SU5 or SO10, they don't work because there are very few representations of associative algebra, and finite dimensional algebras only have one representation. So if you do SU5, you would need to have particles in the 15-dimensional representation, and we cannot have this. It's not a representation of the algebra. So now, if you have a finite manifold, there is an algebra which is MA times M2A, acts as 2 times 2A. Now we enlarge this. A now is so for the standard model A is 2, and we have 96, and the numerology is correct.
So now A is equal to 4, right?
No, A equals, I'm saying, usually A equals to 2.
Yeah.
Now, I made a bold step and I go to 4. You may ask, what about 3? That doesn't work. So for some reason. Now you get 128-dimensional space, 384 taking generations into account. Now, this is the Hilbert space taking into fact that there is what I call the fermion doubling, taking into account that each of these elements is actually a fermion. A fermion in 4 dimensions, a Dirac fermion has 4 dimensions. So the numerology, miraculously, comes out right again. So that's why 3 doesn't work. 3, you get an Hilbert space of a dimension that is of no use. But 4 makes a dimension. So the fermion doubling that was introduced, was discovered, was already there, was discussed and by us in Naples in 1970, no, so not 1990 something. And that I had to project these states out. But this physical redundancy was not explained. And actually, it can be explained because, or it can be necessary, because if you have the spinors times the internal space of 96, it's the same as taking a spinor is 4 times a function, no? And so it's, the dimension of this is 384, which is this 384. So now the game is that, can I still represent this algebra on this Hilbert space without running into clashing? And yes, it took us a long time, but then you can do it. And this is highly non-trivial if one keeps the same Hilbert space. Now the Hilbert space is becoming somehow Smilberg, no? And so the point is that this time the algebra does not actually in a diagonal way on the spinors. It mixes the spinors. In addition, one has to consider a particular form of spectral triple, twisted spectral triple, for which the commutators become twisted by an isomorphism of the algebra. These twisted things now Landius worked on it because it started with Kohn and Moscovici. So they are twisted spectral triples. Okay, I will not write the details of the representation. They are rather involved. The key point is that in the process, you mix Euclidean symmetries, internal symmetry, and gauge indices. So we are in a situation in which there are not yet spinors. So it's a sort of a pre-spin geometric situation. And so in this grand symmetry, the element of df may be negligible. Some of the element of df may be small, and the spinor part in this slash will cause the breaking in a phase in which the symmetry of the phase space emerge. So there is a higher, see, the numbers appearing here, now it's a number. This is a very large number because it's the mass of the neutrino. So to a first approximation, I can ignore all of the other numbers. And I have this pre-geometric phase, and this number here causes the breaking to a smaller symmetry, which is the one of the standard model. So this 4 becomes 2. And there is an added bonus, which is the grand algebra, a corresponding df of d or df operator has more room to operate, because everything here has become a 4x4 matrix. So I can put something there without violating the order 1 condition, but such that the commutator is non-zero, just because the matrix is larger. So I can put it in a corner of this 4x4, but this creates a field all the same. And so I satisfy the order 1 condition. I get d nu. D nu is like df, but with only the big numbers in it. Okay, so I split, because the physical effects of the higher mass is only felt at higher energy. So I split the Dirac operator into a low energy one and a high energy one. When at high energy, only one counts, because the smaller things are correction. When I'm at low energy, only the largest one don't affect, because they correspond to very heavy particles, and only the one. So things are becomes, and then when you do the commutations, etc., you get this sigma field, and it appears before the transition. So this sigma field is somehow something, a field in a pre-geometric phase. I say pre-geometric because I don't have spinors in this. So it's I don't really know what is there. Lorentz symmetry gets mixed up with gauge symmetry. So this is point really to something non-commutative geometry.
Is it related to some phase transitions or something?
Yes, it should be related, although I cannot say anything about the phase transition. I can only say that my symmetries come out correctly. And this field is naturally a very high energy, field. And so this grand symmetry is not ordinary gauge symmetry. So there is no SU8 in the gauge, because the 8x8 matrices mix together how shall I say, the Lorentz indices with the gauge indices. Okay, so, but two of them in one and two of them in the other one. The thing is, well, I don't have. So the fermion doubling was not a problem after all. So it was perceived to be a problem. Actually, there's another final anecdote. There was this fermion doubling, and it was called the fermion doubling problem because it was sort of an unpleasant thing. And Kohn always said, no, this is not a problem, it's not a problem, it's not a problem. Then once I met him, and he came to me very happy, saying, you know, I found a solution to the fermion problem, which was in the Kohn-Markov. So for Kohn, there are no problems. There are only solutions. When I was doing it, was not a problem. Once he found a solution, very good, very good. So there is a solution, but actually it may be a resource. And I finish now. Next time, I will discuss Wick rotation and a little corner of the various Lorentz things. I must confess the next talk is more of a seminar. So while the first 3 lectures, occasionally something I did appeared, next talk is my later work. So I will not much review what other people have done, but I will review something, but So far I've been very fair giving things, but then
So
bit
there,
of
the
analysis.
Lorentz symmetry.
I will discuss the issue of Lorentz, and I will do it with Wick rotations, mostly with Wick rotations.
So you'll be introducing the Klein spaces.
No,
right?
I will do Wick rotations. I will say how I can do Wick rotations.
So Klein space.
I will not introduce Klein spaces because that's my work. Klein spaces is the work of Van Dugen, Eckstein, and so there are various solutions. But I will say something. I will need your pen drive because I will change something in the file. Most probably. Select a reference. The X was introduced even before Kohn and Lott by Dubois Violet, Kernen and Mador. Kohn and Lott is a little bit after. Now, a lot of work has been done by the Marseille group. I should really mention them because although the final version is Kohn, Marcolli, and Shamseddin, Kassler, Yokum, Schuker, and several young people worked on this. And Schuker has really made some, this is a good review. The model has undergone various things. The final cranking with the thing is Shamseddin, Kohn, and Marcolli. Then the unpleasant way is Shamseddin and Ton. And Kohn, Stefan has done work. Shamseddin, Kohn, and Van Sulecom violate the spectra 1. There is a paper on the phenomenon, several gradually can be updated, there are other papers, but by a group around Munich in the US has worked on Patti-Salami non-commutative geometry. The grand symmetry is in Devasado, myself and Martinetti. Twisted spectral triple were introduced in Kohn and Moscovici. I didn't dwell too much around it. There was a detailed link. I could go to something which had gory details, and the twist for grand symmetry is Devastato and Martinetti, and a more recent review on this is Landi and Martinetti. Gianni Landi has worked on this. And that's
Landi,
it.
I think, is going to talk on these things here also.
Yeah, the twist I do twist. Twist is the twisted spectral triples are somehow. I will discuss something tomorrow and in the seminar. It's a fashionable issue nowadays.
Maybe
Okay.
Dr. also knows something on this.
Well, I just want to know the definition, and knows that it's very popular. It's,
Okay, I think we can stop.
Any further questions?
What's the Planck scale?
The scale at which these fields appear, at which this symmetry is unbroken, is around Planck scale.
There are also very strong theorems due to Lachlan orafity.
Yeah, then there Appelquist, no, Coleman Deluc, no. What is
No.
the
Lachlan orafity
yes.
of the all the troubles that come to try to mix internal symmetry with Lorentz group in a non-trivial. The spectrum becomes very complicated. You know, there are
Yeah.
some very strong unphysical features, and there
It's
are
a
a
different.
number of theorems. no?
It's a different phase of space-time, so you cannot use the parameters that you use for this space-time.
Then why is it relevant for low energy physics?
Because when I go down to low energy, I get a field, which is the one that I need to fix the mass of the Higgs. I have an ungeometrical phase. Then the Laplacian basically breaks it, and I go to the field as we know it. But I inherit a field from high energy with a very high mass, and this one fixes the mass of the Higgs and makes the three things go together. And I know that this field must have a high mass. Little problem is that in the seesaw, I get the mass of the right-handed neutrino, which is slightly, well, 1 order or 2 orders of magnitude larger than the one which is expected by phenomenologists. But since they haven't found it yet, I don't care.
The second thing is that you keep talking about doubling, and I remember talking to you about that before.
Yeah, it's quadrupling.
Huh?
It's really a quadruplication, yes.
No. There is a natural doubling anyway, because if you go to Euclidean space, there is a
That's
natural
not the
doubling.
Osterwalder shadow, no.
Huh?
It's not the, it's connected, and tomorrow I will discuss this in detail. It's not the Osterwalder, it's not only the Osterwalder. I'm not, no, so the fair question is, I don't know. Okay, I think that we can let people go to it. Okay. You can clap, but go to it. I prefer not to.